Hi everyone, I want to welcome you to this particular channel once again at the same time to this another lesson edition of video whereby I will want to discuss to you the derivation of Michealis-Menten equation that is used in enzyme kinetics. So, because that has been a challenge for several students, probably in biochemistry or in life sciences at the same time biological science. So, in this video, I'll be talking about the derivation of this formula at the same time how it is applicable to us. So, basically, we all must know that enzymatic reaction is a two-step reaction. The first step is reversible, at the same time, the second step is irreversible. So, where we have that enzyme. So the first step is enzyme plus the substrate, giving us the enzyme substrate complex, and we also have that the enzyme substrate complex giving us um, the enzyme giving us the enzyme plus the product. So this is the first step, which is an equilibrium um, step, and this is the what's it called now? This is the second step, whereby the enzyme substrate complex breaks to give us the product. The rate of this reaction depends on the what on this second step. So the rate determining step is this second step, and with the rate determining step we can write the rate expression or even what we call the rate law. So from this particular second from this rate determining step, that means we can say that the rate, or let's say v rate represented by v, equals to k2. Now each of these stay in form of equilibrium rate constant. This k1, this k2, so this k minus 1, and we have this to be k2. So from that we can say that the rate will be equals to k2, and we have e what es, because the rate of reactions depends on the concentration of the reactant, and the reactant in this second step is the enzyme substrate complex. Now, but in this particular mechanism, described mechanism for enzymatic reaction, this enzyme substrate complex is an intermediate, because by the time you sum up all these reaction steps, the es will cancel the es, and you are only left with what? So the overall reaction will be that you have enzyme plus substrate giving us enzyme and product. So this enzyme substrate complex is an intermediate in this particular mechanism for enzymatic reaction. So its es appearing in our rate law means that we have to do something to remove this what to remove this intermediate in the what in the rate law. So one of the approach that we use that we apply so that this enzyme substrate complex, which is an intermediate, can be removed is what we call the steady state approach. In the steady state approach, we have that the rate of formation of an intermediate equals to the rate of the composition of that same intermediate. So we are saying that steady state approach. So SSA implies steady state approach. We can say that rate of formation of ES of the intermediate ES will be equals to rate of decomposition of the same ES. So from this place now, we can simply write expression for the rate of formation of ES at the same time the rate of decomposition of ES. So from this place now, the rate of decomposition of ES will be equals to, now in this first step, ES is decomposing to give us enzyme and product. At the same time, in the first step, which is an equilibrium step, ES can also decompose to give us enzyme and substrate. So that means we can say that will be what? That will be K2, and we have what? ES plus K, we have minus 1, and we have what? We have ES. So that's the rate of decomposition of the enzyme substrate complex. But in this same mechanism described for an enzymatic reaction, the only point of formation of ES is this equilibrium step where you have along the forward reaction. So that means that RF, rate of formation of ES, will be equals to, that's K1, and we have E, condition of E, and then we have condition of what? Of substrate. That's what we have in this part. So this is the rate of decomposition of the enzyme substrate complex, and this is the rate of formation of the enzyme substrate complex. So combining these two by the steady state approach, we can simply say that the K2, and we have ES plus K minus 1 ES will be equals to K1, and we have concentration of the enzyme over concentration of the what? Of the substrate. So from this place, we can simply say, if we factor out this ES, we can say that ES equals to K2 plus K minus 1, and then equals to K1. We still have our concentration of the enzyme, and we have concentration of the what? Of the substrate. So if I bring together the constants here, I'm going to have K2 plus K minus 1 over, that will be K1 equals to concentration of the enzyme over concentration of the substrate over concentration of what? Of the ES. And that's in a way, so that means, so this constant is what forms our what we call the Km, which is called the what? The Michealis-Menten constant. So that's our K2 plus K minus 1 over K1. So that's how we get this Km, and therefore we can say that Km will be equals to K will be equals to K sorry, Km will be equals to concentration of the enzyme over concentration of the substrate divided by concentration of what? Of enzyme, what's it called? Enzyme substrate complex. Now from this point now, the next assumption that we make is that the total enzyme that we have in an enzymatic reaction will be equals to the sum of the free enzyme, the concentration of the free enzyme, at the same time the concentration of the enzyme substrate complex. That is, the free enzyme and the bonded enzyme are going to give us the total sum of the enzyme that we have in an enzymatic reaction. So we can say that ET will be equals to free E. So these are the free enzyme plus the concentration of the enzyme substrate complex. So if we make this similar formula now, we can simply just write that our Km will be equals to, so we make this E, the concentration of the free enzyme, we make it solve the formula from this expression here. You can simply, and then you replace it with what? So you replace whatever you get with E in this case. That means you are going to have that the concentration of enzyme total minus concentration of what? Of this ES, close bracket, to multiply by the concentration of the enzyme, so of the substrate rather, all over the ES concentration. So that's what we have. So what we just did was to use this particular expression to substitute for this E, which I said is the concentration of the free enzyme. So when you subtract the concentration of the bounded enzyme from the total amount of enzyme, you get the concentration of the what? Of the free enzyme that you have. And you can simply use this expression to remove this E with and replace it with ET minus concentration of the enzyme substrate complex. So from this place, what do we do? So let me start from here back. So from this expression, if I cross multiply, if I do a cross multiplication at this point, that implies I'm going to have that ES, concentration of this ES times Km, to be equals to, that will be, at the same time I open up this bracket, that will be what? That will be concentration of the enzyme total, and we have concentration of what? Of S minus concentration of the enzyme substrate complex, and we have concentration of the what? Of the substrate. So if I collect the lactams, this one have ES, this one also have ES, and that means I could have that my ES, concentration of the ES, and then we have Kn plus concentration of what, of ES, and we have S to be equals to concentration of the enzyme total, and we have this one to be what, to be this. And that implies that I could say concentration of ES into bracket Km plus concentration of the substrate equals to concentration of the enzyme total, and we have S here. So if I make this ES of the formula now, if I make this ES, that means I could say that concentration of the ES, concentration of the enzyme substrate complex will be equals to concentration of the enzyme total times concentration of the substrate all over Km plus concentration of the substrate. So this is what we have as the expression for this intermediate. You know, I said something the other time that for this rate law or for this rate expression, intermediate must not be there. So, and we apply the steady state approach to be able to get an expression for this intermediate, and so that we can remove it from this expression. So now we already got that particular expression that we need, and therefore I will now substitute for this concentration of the enzyme substrate complex in this rate law. So by substitution, by substitution, by substitution, by substitution, I'm going to have that the rate, which is V, will be equals to K2, and I will have concentration of the enzyme total and concentration of the substrate all over Km plus concentration of the what, of the substrate. So from this list, this is the expression that we have for so this is the expression that we have for the rate of reaction in terms of what, in terms of this rate constant K2, total enzyme concentration, the substrate concentration, the Michealis-Menten constant. At the same time we have this, and this expression that we have. But it is believed that velocity becomes maximum when all the enzyme involved has become bounded to the substrate. That is, when the enzyme becomes saturated. So in a way, Vmax will be equals to K2 times what, the total enzyme this time. So the Vmax appears when the what, when you have the total enzyme already bounded to what's it called now, to the substrate, at which point so all the enzyme will have been binded to a substrate, and that's where you have the maximum velocity, and therefore we can say that our V will be equals to Vmax, and we have substrate concentration over Km plus this expression. So this expression that we have here is what we call the Michealis-Menten equation, which is used in enzyme kinetics. So I think with all of this thing I've done now, I'll be able to show you how to derive the Michealis-Menten equation. But please take note of some important parameter in this particular expression. First, the Vmax. The Vmax shows us the maximum possible rate of an enzymatic reaction. Km tells us about the substrate concentration when the velocity is half of the Vmax. At the same time, it is also an indicator of the affinity of an enzyme for different substrates. And the rule is that the lower the Km, the higher the affinity. At the same time, another important thing to also take note is the total amount of enzyme. At the same time, this rate constant. The rate constant here is defined as the turnover number, and it is the number of substrate molecule converted to product when the enzyme is completely saturated. That's this case. So in case they ask you to probably calculate a turnover number, you can always work around this. Now, it is this Michealis-Menten equation that was linearized in order to get the Lineweaver-Burk equation. So the linearization of this equation by Michealis-Menten gave us the Lineweaver-Burk expression, which help us to get a straight line graph when we plot the reciprocal of velocity against the reciprocal of substrate concentration. So in most cases, when you plot a graph with this expression, that is to plot the velocity against substrate concentration, the graph of Michealis-Menten equation will look like this. So this point is the point where you have the Vmax. This is where you have the Vmax. This Vmax. So let's say this is your Vmax over 2. If this is Vmax over 2, so you can just trace that to this point on the curve on the graph and then trace it down, and that will be your Km. So this is V against substrate concentration. So for Michealis-Menten graph, this point whereby the velocity is no longer increasing with increasing concentration is your Vmax. And when you find the half of Vmax and you trace it back to this curve, and you find the corresponding value horizontally, that will be your Km. Like I said, Km is the substrate concentration when velocity is half of the Vmax, and that's that about the Michealis-Menten equation. And like I said, you can linearize this expression to get your Lineweaver-Burk equation. In short time, let me quickly just show you how to do that to get the Lineweaver-Burk expression. Now we have V equals to Vmax, and we have substrate concentration over Km plus S. So from here now, if you take the reciprocal of both sides, that means you can have 1 over V equals to, that's Km plus S all over Vmax, and we have X. So this is this expression is the reciprocal of this, and this is the reciprocal of this. So from this place we can have that 1 over V will be equals to Km over Vmax, and we have substrate concentration plus, and then we have substrate concentration over Vmax, and we have substrate concentration. This we cancel this, and then we are going to end up with 1 over V equals to Km over Vmax, and we have 1 over substrate concentration plus 1 over Vmax. So if you relate it, so this expression that I got here is the Lineweaver-Burk equation, and through this expression you can get a straight line graph when you plot the reciprocal of velocity against the reciprocal of the substrate concentration. So in Lineweaver-Burk plots, the graph of enzymatic reaction usually produce a straight line graph. That is, you have something like this. So this is 1 over concentration of what? Of S, and this is 1 over V. So when you plot that graph, you have something like this. So this point is the y-intercept, and that's where you have the 1 over V max. So this point is the y-intercept, and that's your 1 over V max. While the slope of this line equals to Km over V max. So when you find the slope of this straight line, you can easily equate it to your Km over V max. But because you have gotten the V max from the y-intercept, you can simply use that to get the Km from the slope, and that's how to work with this particular both Lineweaver-Burk expression and its graph at the same time, Michealis-Menten expression at the same time with its graph. So I believe with this video you are able to capture how Michealis-Menten expression was derived together with the Lineweaver-Burk expression. At the same time, you are able to also how to get Vmax and Km for both from both Lineweaver-Burk plots at the same time from Michealis-Menten plot. In the subsequent video, I hope to also go further into discussing different kind of inhibitions that we can have, talking about your competitive inhibition, non-competitive inhibition, and uncompetitive inhibition, so that we can have an idea of how to get all these enzyme kinetic parameters as touching inhibitions. So at this point, thank you for watching this particular video. I hope that if you have any question, you will do it, or suggestion, or even comments, you will do it to drop it in the comment section, or try to chat me up privately, and I will also be glad to respond to your questions, at the same time your suggestion too, so which will also be of help to us in make much better video content which can be of help to you. And please do not forget to subscribe and share this the link to this channel and to this video with your friends and colleagues which you know can also be in need of this particular video. And at the end of this video, you can do well to subscribe if you have not subscribed. So please click the subscribe button. Thank you.